This is a similar question to the previous one, and it's where we are going to try and calculate the work done in another cycle. So air at an initial pressure of 0.1 megapascals and a temperature of 55 degrees is enclosed by a cylinder and piston. Its initial volume is 0.001 meters cubed. It undergoes a thermodynamic cycle consisting of 4 processes. So first of all, it's got a polytropic compression with an exponent of 1.4, where the volume is reduced to 1/10 of its initial volume. The pressure then is increased to 2.4 megapascals at constant volume due to heat addition. And then the air is brought back to its initial volume in another polytropic process with the same polytropic coefficient of N equals 1.4. The air is then brought back to its initial state at constant volume process due to heat removal. So once again, very similar to maybe like an idealized petrol engine cycle called the Otto cycle, where you've got compression and then you've ignition, which is the pressure going up dramatically, and then you've got the power stroke, which is the expansion of the cylinder, and then you've an exhaust. In a real petrol cycle, it'd be a little bit more complex than that. So what we need to do, rather than try and plot the curve, what we needed to do was find a constant in the polytropic expression in order to plot the curves, but we're not going to plot the curves. What we're going to do is make sure that we have the volume of pressure at each of these 4 states, and then use that to calculate the boundary work, and then from that, the power as well. So we have the volume and pressure at the beginning. We need to know the volume and pressure at state 2, and we're told that the volume at state 2 is 1/10 of the volume at state 1. So we can work that out, and then we can use the polytropic relationship to find a P2. P3 equals P2, and we're told the pressure at P3 is 4.2 megapascals. So once again, we use the polytropic expression to help us find P4 down here, and V4 is the same as V1, so it's 0.001 meters cubed. So we can see our unknowns in there. So we calculate the work done during each process, first of all, calculate the work output per cycle, and then calculate the average power output if there are 2,500 cycles per minute. So let's first of all calculate V2. So V2 is simply V1 divided by 10. So it's 1/10, and it's 0.0001 meters cubed. And then we use the polytropic expression V1 multiplied by, or P1 multiplied by V1 to the power of N equals P2 multiplied by V2 to the power of N. Transpose this to get P2 on its own. We have P1, and we now have V1 and V2 and the polytropic exponent. And P2 works out to be 2.512 megapascals. So now we have V2 and P2. So for process 2 to 3, it's a constant volume process. In this process, the volume remains constant while the pressure increases from 2.5 up to 4.2 megapascals. Since the volume is constant, we know that V2 equals V3. So now we have V3 and we have P3 as well. The polytropic expansion. Once again, we use this relationship P3 by V3 to the power of N equals P4 by V4 to the power of N. And since V4 equals V1, we can now solve for P4. So we have V3 and V4, and we have P3, and P4 works out to be 0.167 megapascals. And finally, in this final process, the air is brought back to its initial state at constant volume. So the volume remains constant. So now we know that V4 equals V1, which is 0.001. And the pressure returns to its original pressure, which is 0.1 megapascals. So we have the pressure and the volume, at all states. And with that, we can put them into our polytropic boundary work equation. So between states 1 and 2, for that polytropic compression, it's P2, V2 minus P1, V1, 1 minus N. And it turns out to be minus 0.00038 megajoules. We'll tidy up the megajoules at the end. Constant volume heat addition. So constant volume, the boundary work between states 2 and 3 is 0, and it's the same for process 4 to 1. So for 3 to 4, we use the polytropic boundary work equation, and it's P4 V4 minus P3 over V by V3 over 1 minus N. And it turns out to be 0.00063 megajoules, which is positive because it's an expansion. So we basically add all them together, and we get 0.00025 megajoules, which is just 250 joules when we tidy it up. And if we want to know the net power being produced by the system, we multiply it by 2,500 cycles per minute, but divide that by 60 to get into cycles per second, and we have 1041.6 watts, and we tidy that up and we get 10.416 kilowatts. So what we're going to do now is going to introduce the general energy balance for closed systems. So a small recap from an earlier chapter. The first law of thermodynamics states that energy can't be created nor destroyed. During the process, it only changes form. So we apply that to thermodynamic system, and we say that the total energy entering the system minus the total energy leaving the system equals the change in energy of the system. So we're accounting for the energy somewhere. It's going in, it's going out, or it's still in the system. In equation format, it looks like this. If we take the right-hand side of that equation, we can say that the change in energy in a thermodynamic system is either a change in internal energy, change in kinetic energy, or a change in potential energy. And for stationary systems like the piston cylinder system, we can generally say that we're only dealing with the change in internal energy. If there is a kinetic or a potential energy aspect, they're usually very small and negligible. So now we look at the other side of the equation, the energy in and the energy out. And we know that that can come in three forms: a change in heat, change in work, or a change in mass flow. In open systems, we're dealing with mass flow, but in closed systems like the piston cylinder system, there's no mass flow. The working fluid's not coming in or leaving the system and crossing the boundary. So for a stationary closed thermodynamic system, the first law, the classic statement of the first law of thermodynamics looks like this. And what we're basically saying is the heat added to the system minus the work done by the system equals the change in internal energy in the system. So the energy is either going in there in the form of heat, coming out in the form of work, or it's in the system in the form of internal energy. And we can also say for a cycle that the energy in minus the energy out equals the change in the system, but for a cycle that should equal 0. So the energy in equals the energy out. So what we can say is the net heat in equals the net work out by the system, or vice versa. And the net heat transfer rate equals the net power out of the system, or vice versa. So a few examples of all this. In the compression stroke of an internal combustion engine, the heat rejected to the cooling water is 45 kilojoules per kilogram, and the work input is 90 kilojoules per kilogram. Calculate the change in specific internal energy of the working fluid, stating whether it's a gain or a loss. So this is our standard classic statement of the first law. We're dealing with specifics here, so we're going to express it like this in kilojoules per kilogram. We know that the heat coming out of the system is minus 45 kilojoules per kilogram. So if heat is leaving the system, it's minus. We know that there's 90 kilojoules per kilogram of work done on the system. If it's done on the system, it's taking energy from the environment to do that. So we put that in as a minus. The double minus will make a plus. So ultimately, we're left with a 45 kilojoules per kilogram of change in internal energy, specific internal energy. So that should be a small u there. So basically, 90 is going in, 45 is going out. So we have 45 left in there. Another example, and this is one that we done earlier on, and we're just going to continue it on. The piston cylinder device contains 0.4 meters cubed of air at 100 kilopascals and 80 degrees. So that's this point over here, and this is what it looks like. The air is now compressed to 0.1 meters cubed in such a way that the temperature inside the cylinder remains constant. Determine the following: the work done during the process. So we calculated the boundary work was minus 55.5 kilojoules. So it's compression work done by the environment. So it was a negative value. What we need to know now is the heat flow during the process. And we're going to apply the classic statement of the first law. Because it's an isothermal process and the temperature doesn't change, the change in internal energy equals zero. So we have zero over here. We have minus 55.5 here for the work. The double minus makes a plus. So ultimately, the heat is going to be minus 55.5 kilojoules. So we put in 55.5 kilojoules of work. The internal energy doesn't change, so 55.5 kilojoules of heat comes out. This is another example here where piston cylinder device contains air at 150 kilopascals and 27 degrees. So down here, at this state, the piston is resting on a pair of stops, and the closed volume is 400 liters. So that's the piston there. As we increase the pressure to 350 kilopascals, the piston doesn't move off, it stops until we reach 350. And when we reach 350, the pressure stays constant and it lifts the piston off, it stops. And it's during this second process here, work was done. And we calculated that work to be 140 kilojoules. What we want to know now is the total heat transferred to the air in the system. To find that, what we need to do is we need to find the specific internal energy here. And to do that, we look up the property tables for air. So at 300 degrees, the specific internal energy at 300 Kelvin, is 214.07 kilojoules per kilogram. And then it's illustrated here, and then the other one, which is not illustrated, is the specific internal energy at 1400 Kelvin equals 1113.52 kilojoules per kilogram. Now what we need to know is we need to know the mass, and we can use the ideal gas law, PV equals mRT, transpose it to get M on its own. We have the initial pressure, we have the initial volume, we have the specific gas constant for air, and we have 300 Kelvin. And that works out to be 0.697 kilograms. So we have the mass with the specific internal energy. So that will give us the change in specific internal energy. So that will give us the change in internal energy once we multiply it by the mass. We have the work done, which was positive. And when we put that into the classic version of the first law, it works out to be 767 kilojoules is the heat that was added into the system to make that happen. So we've 767 going in, we've 140 going out in the form of work. So we have 627 left there in the system. Another example, a rotating paddle wheel rotates within water. 195 kilojoules of work is done on 3 kilograms of water, which is initially at a temperature of 18 degrees and a pressure of 1 bar. Heat transfer also occurs. What is the net heat transfer for the process if the water reaches a final equilibrium temperature of 25 degrees at the same pressure? So we have our classic statement of the first law. We just elaborate on the change in internal energy. So that's mass by the change in specific internal energy. We have the work, and what we want to know is Q. So to get the specific internal energies here at 18 degrees on the steam tables, we have to interpolate between 15 and 20. Just note that this is a different version of the steam tables, and it's referring to A1. So at 18 degrees, we use the specific internal energy for saturated liquid at 18 degrees for compressed water. And it's 75.5 when we do the interpolation. At 25 degrees, we have the saturated, the specific internal energy for saturated liquid is 104.83. So now we have the mass, we have the change in specific internal energy, and that works out to be 87.9 kilojoules, which is the change in internal energy. We put that in over here. We have the heat that we're looking for. We have the work going in as a minus value because it's work going into the system. The double minus makes it a plus. So the heat works out to be minus 107.1 kilojoules. So that's leaving the system. So we put in 197 in the form of work, minus 107 leaves the system, and so we're left with 87.9. Another example here, calculate the rate of energy transfer to the surroundings from the internal combustion engine, which burns fuel at a rate of 5 kilograms an hour, while it produces 20 kilowatts of output power. The calorific value of the fuel is 40,000 kilojoules per kilogram. So we want to know what the energy is going into the system in the form of fuel. So the mass flow rate of the fuel is 5 kilograms per hour. We divide that by 3,600 to get kilograms per second. And then the calorific value is 40,000 kilojoules per kilogram. So we multiply those two together, the mass flow rate of the fuel by the specific, the calorific value, of the fuel. The units cancel and we're left with kilojoules per second, which is kilowatts. So we have 56 kilowatts of energy going in the form of fuel. We're told that we have 20 kilowatts of power coming out, and the difference between the two is the heat loss, which is 36 kilowatts. So you can see over here the illustration, 56 kilowatts going in the form of fuel. We have 20 kilowatts going out in the form of power, and then we have 36 kilowatts, which is lost to the environment in the form of heat. And if we want to know the efficiency of that, we'll not ask for it in the question specifically, but it will be the output power over the energy going in, which works out to be approximately 37.7, which is about the range for petrol and diesel engines, the efficiency range for petrol and diesel engines. Another example here, in the cylinder of an air motor, the compressed air has a specific internal energy of 420 kilojoules per kilogram at the beginning of expansion, and specific internal energy of 400 kilojoules after expansion. Calculate the heat flow to or from the cylinder when the work done by the air during the expansion is 100 kilojoules per kilogram. So air motors are used to produce continuous rotary power from a compressed air system. They provide a number of advantages over electric motors. Because they do not require electrical power, air motors can be used in volatile atmospheres. So the air is coming in, it's rotating those vanes, and that rotates the shaft and does some kind of shaft work for us. And then the air goes out this way. So the change in internal energy from the inlet to the outlet is 220 kilojoules per kilogram. And that produces 100 and, or, excuse me, 200, 100 kilojoules per kilogram of work coming from the shaft. So the remainder of that then, the 220 minus the 100 is 120, and that's the amount of heat leaving the system in the form of kilojoules per kilogram. So those last two examples are, strictly speaking, open systems. So we can still apply the first law to them because we're only being asked to work it out in terms of internal energy. But generally for open systems, we would apply the steady flow energy equation. So we'd be taking into consideration enthalpy rather than internal energy and the velocity and any potential energy aspect as well. So this is basically applying, in this section, we've applied the first law to closed systems. And what we're going to do in the next section, described as the conservation of mass and energy, is we're going to apply the first law to open systems. And that's where the steady flow energy equation comes into play.